So, statistical significance, just like everything else in this class pretty much, uses a normal curve. So we do have some conditions. Do you guys remember the example that I gave you for this when we talked about it originally? I said soda manufacturer puts 20 ounces of soda in their bottles, right? And we talked about what if it's not filling completely or filling too much. So let's use that example. So here is the claim that the company makes that 20 ounces is how much their bottle is filled with. So that's our null hypothesis, that mu equals 20 ounces. And I'm going to not pick on Coke today. Let's pick on Pepsi. Let's say that I'm an avid Pepsi drinker. John. I'm an avid Pepsi drinker, and I want to make sure that I'm not being screwed. So I take a sample of Pepsis, a large sample, say, I don't know, 30, 40, something like that. And I measure every one of the bottles. And I want to see if there's if I'm getting significantly less Pepsi, because I suspect that I've been getting less Pepsi than they're promising me, okay? So what I have to do is I have to set a fence. It's called alpha. I'm going to set a fence that is the boundary between them giving me enough soda or me saying, wait a minute, the Pepsi man is screwing me and I'm going to take him to court and win millions of dollars, okay? That fence is called alpha, and you get to set it. We set it based on usually these values. There's a correlation between our alpha value and these confidence interval values. The three common ones are 10%, 5%, or 1%, which are sort of the converse, if you will, of these values, right? So, and in effect, these guys still apply. If you're using a 1% alpha, you're probably looking at something pretty serious, okay? If you're looking at 5%, you better be at least 5% or less if you're going to take your data into court of law. Or if you're worried about being sued, you better be checking yourself at 5% or less. And 10% is pretty high. I mean, something that happens 10% of the time is relatively common. You wouldn't use an alpha that's less than 10, and usually we don't use one that's less than 1%. So those are the three common ones, 10, 1, and 5. I'm going to say 5% here. I'm going to say that the alpha is at 5%. So what that means for us is that if we take our data and we standardize it, and we find that our data falls on the tail side of our fence, then this data, this is significant. We call this significant. By the way, fence is my term, that's not a technical term there. If we standardize and we find that our data falls anywhere else, this would be not significant. So I take my information, I standardize it, and I find that in 20% of all samples of my size, I could expect my bottles to be filled as low as they are. That would put me out over here somewhere. That would be a not significant. Significant is when you get into a tail where something is happening and it's very unlikely that it happens. Okay. All right. And what we do is we use our p-value. is going to be somewhere on one side or the other, or it could be right on the line, and we compare the p-value to our alpha. So here's how this works. If the p-value, remember what the p-value is, that's the number you get off table A for your probability. If the p-value is less than or equal to alpha, I'm out of practice of drawing alpha, I need to get back into practice, then there is significant evidence against the null. Significant evidence against the null. Hey, you're saying that your bottles have 20% or 20 ounces in them, and I found that my bottles only had an average of 19.25 ounces. And that, by my calculation, is significant. So I'm taking you to court. I want my 0.7 ounce of Pepsi back, right? Okay. And there's some very specific phrasing that when we answer a question like this. If this is true, if the p-value is less than alpha, we say that we reject the null that's our HO. Okay, hold on, we got to stop right there. Yes, I really am only about 10 years old in mental age. You get to learn in this class how to reject the hoe, right? We're rejecting the hoe, okay? You would put some context here, you know, whatever the context is that we're talking about, and accept the alternative. And you'd probably put some context maybe here. So remember in this class, whenever you're answering anything, especially for a test or the AP test, to answer 5 may be the correct numerical answer, but if you don't put context to it, you're going to get hit pretty hard. So context is important. In addition to that, let's get our quotes in there. In addition to that, if the p-value is less than alpha, or equal to, less than or equal to alpha, we say the data are statistically significant at level alpha. The data are statistically significant at level, and whatever your alpha level is. You don't necessarily say at level alpha, you just say, you know, at 5% or 1% or 10%. Yeah, Leo.
Do you put right greater than or less than the p-value did on both of them?
No, it's the same idea.
Okay, same idea.
So you're rejecting the null and saying that it's significant. You're in the significant category here. Yeah, you're going to be less than your alpha. Okay? We'll do the greater than here in just a second. So the test for this, I think we wrote this. I think we wrote it down the other day, but maybe not quite in the same way. The z-test for this, and if it's a z-test and it's counts, then that means we know sigma, right? For population mean. is z equals x bar minus, that's not a very good minus, minus mu sub naught, we say mu sub naught, I'll define that here in just a second, divided by sigma over root n, right? That should be pretty familiar, right? Except that mu sub naught. Well, the mu sub naught is just the mu of the null. I didn't do a very good mu there. There we go. Fix that. And the mu sub naught is the claim. In my example, Pepsi claims that they're giving me 20 ounces. I don't believe it, so I'm going to double check it, right? Probably not. I don't see myself winning millions of dollars on a claim that Pepsi's not giving me enough soda. Dang it. It's fun to talk about, but I'm not really Sue happy either. What's that? Yeah, you might get a little bit. My guess is you would never find a statistically significant sample of Pepsis that weren't filled close enough. Yeah, you'd know. I just don't think you'd ever get that. Okay. Everybody all right here with this? Or at least, are we still writing? No? Okay. So last year I wrote on the board, reject the hoe, and the next thing that we're going to learn is fail to reject the hoe, and my freshmen just about freaked out when they saw that. They wanted to know what was going on. Like, well, if you come take stats, I get to teach you how to reject the hoe.
You don't know what's going on. You don't want to know.
Well, maybe some of them do, John.
Just say drop out now. It's not worth it.
I'm afraid of what John might write for his senior quote. I'm afraid it might have something to do with my class. I know. That's a bummer. What if the p-value is greater than sigma, alpha? So what this means is that you're in the not significant part of the curve. It's not statistically significant. It's nothing you could take to court. It's nothing that really you would make a comment about. So, but we still have some specific phraseology for this. We fail to reject the null. And conclude there is not significant evidence against it. Yeah, John.
So I'm a little confused about like the p-value. So is it something? So when you're doing test, how do you know? Like, how do you figure out the p-value you need to see if it contradicts the hoe or the hop?
The null,
Yeah.
the null, the hoe, yeah. That's a good question. So how do you know? Well, first of all, you set the alpha. You set that fence, that border that you're either going to be on one side or the other generally. Standardizing, take the z-score, turn it into a probability, and then that's your value. Yeah.
So will they always give us like a confidence interval because you said that it throws up?
It's not a confidence interval. It's a significance test, but it uses the same sort of idea as the confidence interval and many of the same calculation values.
10, 5, and 1.
Mm-hmm.
Will always be the same?
No, 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 no. Your alpha will probably be something you have to choose. That's why I'm telling you, if it's 1%, it's kind of a life and death sort of situation. If it's something important that you're afraid you might get sued over or you want to sue somebody with, 5%.
Oh, so you're just telling like examples that we can.
Exactly. Where and when you would use each one. Now, the three most common ones are 1, 5, and 10, but it could be anything.
Okay.
You'll never really see 1 over 10%.
Okay.
Anything more than that's way too common of an event, so you wouldn't use that. And usually, if your p-value is less than 1%, you say that it's statistically significant at any reasonable alpha.
Okay.
So, right, if it's less than 1, regardless of where you set your alpha, it's going to be significant. Okay, one more little sentence here. Never accept the null. You can reject or you can fail to reject, but you never accept the null. Here's why. Let's say we're going back to the 20-ounce situation. Let's say I find a sample of Pepsi's and I set my alpha at 5% because I want to make sure that if I find the right data, if my data works out right, I'm going to make myself millions by suing the Pepsi company, right? So I set that at 5%. And then I calculate my p-value. So anything over here, in this case, this would be a less than. Anything over here, any p-value that I get in here would lead me to maybe go hire a lawyer and sue them, right? But let's say that I'm not quite there. Let's say that my p-value is really close. But it's not less than that. It's 0.051. Okay? I'm so close, I can taste the legal lawsuit going on here. But my p-value is not low enough for me to reject the null. Now, does that mean that I don't have evidence that they're not putting enough Pepsi in the bottle? I mean, I'm like right here. No, I think it definitely in this sample it shows that they were underfilled. There's evidence that there's underfilling going on. But is it underfilled enough for me to take them to court and win a court battle? No. Okay? So this is why we never accept the null. We simply fail to reject it. Because by accepting it, you're saying, oh yeah, I didn't find that they were underfilled at all. Right? When in fact, maybe I did find that they were underfilled. They just weren't quite underfilled enough for me to lower the hammer down on them. Right? Does that make sense? So that's why we never accept the null. If you write this on a test, I accept the null, then yeah, it's going to ding you, especially if it's the AP test. You fail to reject, or you reject. You fail to reject or reject. Okay, let's look at a problem. See if some problems will help clarify this. So what are we really doing? We're just standardizing. Okay, page 698, problem 11. Yeah, 1111. Coffee sales. This says weekly sales of regular ground coffee at a supermarket have in the recent past varied accordingly to a normal distribution, with a mean mu equals 354 units per week and a standard deviation of 33 units. So they're giving us that it's normal. Mu equals 354. Yeah, units, I don't know what a unit of coffee is, per week. I don't know if it's pounds or pallets or what exactly. And sigma is 33. So standard deviation is 33. It says the store reduces the price by 5%. Sales in the next 3 weeks are 405, 378, and 411. Is this good evidence that the average sales are now higher? So they give us the null and the alternative hypothesis. They say the null hypothesis is that the mu is unchanged. Okay? That's the claim. That's the status quo. The average has been 354 per week. We think, or we want to know, is, was the average greater than 354? Now, it's pretty clear to see that, in fact, they are. The average would be greater, right? All three of these numbers are greater. If I average these three out, it's going to be more than 354. But the question is it statistically significantly higher? Was it significantly higher? We'll see. I don't know. So the first question is, what's X bar? So how do we get X bar? Add them up, divide by 3, right?
398.
398, okay. I think you're correct there. So we add these 3 weeks up, divide by 3. So what's N? Yeah, 3, right. So we've got X bar, we've got mu, we've got sigma, we've got N, we've got everything that we need to standardize. B says, sketch the normal curve for the sampling distribution of X bar when the null hypothesis is true. That's telling you where mu is. So if the null hypothesis is true, that means that 354 is our average there. Why is the sampling distribution normal? Are the other conditions satisfied? How do we know it's normal? It's given, right? Isn't it given? Mm-hmm. Yeah, it's given. How about independent? Do you think the weeks are independent? Yeah, I think the reasonable to assume weeks are independent. How about SRS? It doesn't say, you're right. So they've taken a sample of 3 consecutive weeks while this coffee is on sale. I believe that's an SRS. If you're kind of questioning it, that's good, because I think it is questionable. And here's why we would assume that to be an SRS. Remember back when we talked about SRSs a little bit ago, and it said that if a biologist, say, is taking a sample of beetles, let's say, out of the environment, and let's say you're the biologist and you go into your backyard and you collect 30 beetles out of your backyard, that's generally accepted to be considered an SRS, because you can't like number all the beetles in Boise and then draw an SRS of the numbers and go find the beetles that are numbered those numbers, right? That's not realistic. Not only that, what we're really concerned about here is, did the sale influence the price? So we have to use those sale weeks. So this would be generally accepted. I would say that this the assumption is accepted on kind of the same grounds as pulling beetles out of your backyard for a sample is acceptable as an SRS. Okay? So assume weeks chosen are an SRS. Okay? Guys. John, I got a foursome back there. Do I need to move that foursome?
No, we're good. I wasn't talking.
Not at that
Not
moment.
at that moment, yes.
Okay. All right. So let's standardize. So we've got X bar is 398 minus the mu sub naught. That's the claim. The claim is that the average should be 354. Divided by the standard deviation, divided by the sample size, which is square root of the sample size, 3, right? So we want to get the test statistic, the z-score on that. I'll let you guys.
2.309.
2.309, you want to round that for me?
2.31.
There you go. Yeah, so 2.31 is the test statistic, which we also know as Z, right? And now we want to calculate that probability, so we go to table A and look at 2.31. You're going to find that that's 0.9896. Now, we haven't set an alpha. It hasn't really said to do that yet. Yeah, John, what's your question?
I got the wrong Z value. I got 2.25.
2.25. Here's what I would say. Do 398 minus 354 equals, and then divide that, open a parenthesis. So parenthesis 33 divided by root 3, close parenthesis. I suspect there's just an order of operations. See if you can get it. Okay, this is a greater than. The examples that I gave in the notes were less than. So that means that we're looking at some number greater than, but we've got to set our alpha. We've got to set our fence. I don't think it's life and death, so I don't think we need an alpha of 1%. Okay. Could somebody lose their job over a miscalculation on this? Perhaps. So maybe 5% is acceptable, all right? Or you might go, coffee sales isn't that big a deal. Maybe 10% is okay. So I wouldn't choose 1%, but I think it comes down to between 5 and 10. I'm going to go with 5. 5 is a good, safe alpha score. So we're going to say alpha is 0.05. Okay? Now it's more than. What do I have to do to my probability? Got to do 1 minus, right? So anytime it's the upper tail, we're going to do 1 minus. So 1 minus the 0.9896 is going to be 0.0104. This is the p-value. Okay? That's the p-value. And what we do is we compare the p-value to the alpha that we set. So 0.0104 and 0.05, which one's bigger? The 0.05 is bigger. So if the p-value is less than or equal to alpha, we reject the null and we say that in fact, yes, we have significant evidence that the coffee sales are greater, because our p-value is going to put us somewhere over here. Does that make sense? So we're in the tail. So D, we have significant evidence to reject the null and conclude coffee sales were higher. Good? Okay. Let's look at one more that's just a little bit more, just kind of practice oriented. Give you guys a second to catch up on that. Everybody got it? I'll take that. Silence is a yes. Okay, page 701, number 1115, significance tests. In this, they give us a null and alternative hypothesis. The null hypothesis is that mu equals 0. The alternative is that mu is greater than 0. And the question for A is, what values of z would lead us to reject the null at alpha is 5%? Well, let's take and look at a curve. So the null hypothesis is that 0 is our value for the null. Our alpha is set at 5 and it's a greater than problem. Mu is greater than. So that's going to put that in the upper tail here. So alpha is 0.05. So that means that 5% of the data, or 5% of the time, we would be statistically significant with whatever sample we're taking. What percent of the time would we not be statistically significant? 95, right? The other part is 95. Now there's a very direct correlation to this and the z-scores that we learned about confidence intervals. Without looking at table A, could you tell me what z-score would go here?
1.96.
Not 1.96. It's not negative, it's on the positive side of things. If we're talking about a confidence interval, right, going back to the confidence interval idea, you have tails in each one, right? So it's looking for the numbers between. Well, this is a single tail. If it was a double tail, how much data would be between? 90, right? So thinking of it that way, if I had another tail here, 90% would be in between, and we would have a z-score of 1.645. Because if this was a confidence interval, it would look like this. 90% in the middle, 5% at each tail. And this is plus and minus 1.645, right? That's your 90. Do you see the relationship? It's that 5% in the tail. If not, that's okay. Look at table A. Try to find 95%, and you'll find that value. You'll probably round it a little differently, but that's there. Okay, B. So the null hypothesis in B is the same, but the alternative changes. The alternative becomes mu does not equal 0. We're still at a significance level, alpha is 0.05. And we want the z-scores. Now, if it's not equal, that's a two-tailed significance test. It's kind of one of those, I don't really know if it's more or less, but I think it's not what they say it is. So I'm testing to see if it's too much or too little. I don't have an idea. So in this case, it's two-tailed. And 0 is still here. The 5% gets split into two parts. So in each tail, we'd be 0.025. So how much is in between those two tails? 95%, right? Or 0.95. So what is the z value here and here?
1.96.
This one's 1.96, right? So when you deal with your alpha, if it's a two-tailed test, you split alpha. Alpha is the percent of the curve that you're looking at to make significant. But if that percent is in two tails, then you have to split that alpha between the two tails. It's an equal amount in each tail. So the last question on this one is, let me get to this one. It says, explain why your answers to part A and B are different. Well, on tests where the alternative hypothesis is mu does not equal something, this is a two-tailed test because you don't know if it's greater than or less than. So the total area of alpha is split between the two tails. So you split alpha, you half alpha when it's a does not equal significance test. I had kind of a hard time keeping that straight. I hope you don't. Alpha is always a certain percent, whether it's in one end, the other end, or split between the two. Yeah.
So for the first one that we did, we just like, because we said there's 5% on one side and then 5% on the other, so then it would be 1.645 or whatever, around that. Would you always do that in one case, just like, but so like whatever we have as a percentage, we just either
Sort of.
everything.
I think, so I think where you're trying to get me to clarify for you is there's really not a second tail here in the problem, right?
Yeah,
But if you can think of it in terms of a confidence interval where it does have two tails and you've got 5% in each tail, that's what you'd have to have because they'd be equal, right? Then oftentimes you can go back to our confidence interval values that I'm kind of hoping that you guys get memorized and use that value without having to go to table A. It's just kind of a shortcut if you can use it as a mental shortcut. But if you're using table A on that, what you would do is you'd go, and I think 95% is in, you'd look at the lower part, right? So I'm going to look for 95%, which is in a darkened region here, but it's basically between 1.64 and 1.65. And so you can get it from there as well. Yeah, that's completely acceptable, and I guess I like shortcuts. And if you understand the shortcut, then you understand this a little bit deeper, right? Okay. So if you don't understand the shortcut, or if you're not quite there yet, that's okay. Just pull table A and look for that z-score. So if you said 1.64, I'd accept that. If you said 1.65, I'd accept that. Okay? Yeah. All right.